Thank you. Need to turn. All right, welcome back, everyone. Sorry for the delay. We always trying to figure out things with this new system. And welcome everybody again. And it's a pleasure for us to have Kunyan today, who is visiting from Florida State University. And he's an expert in topological phases of matter, especially in fractional quantum Hall, where he made some seminal and important contributions in collaboration with his longtime partners, Duncan Haldane and Edresai. And today he's going to be telling us about the interplay between topology and geometry.
Oh, thanks a lot, Adrian, not only for inviting me to give this talk, but actually for starting this entire, is this on? No, it's not on. Ah, okay. It's on now, I guess?
Now
yeah.
it's on.
Good,
Probably
good,
no
good.
one heard the introduction. Okay.
That's okay. That's fine, yeah. Well, okay, so again, thanks, Adrian, for not only inviting me to give this talk, but also to start this seminar series some 2 years ago, which to me was the very first online seminar series, which actually kept me, give me some sanity during those lockdown days. So I guess to some extent, today is my opportunity to pay back, to actually contribute to the series. Okay, so everybody sees my title on the screen. So obviously this is a talk on quantum Hall effect, especially fractional quantum Hall effect. So let's see, how do I flip the, okay, so I'm not able to actually, okay, here we go. Okay, so I don't really need this. So like most quantum Hall talks, I also start with this plot, which I'm sure you have seen many, many times. Now, if I were giving a colloquium, I would be bragging about the 2 Nobel Prizes associated with both the integer sequence on the left and the fractional sequence on the right. But this is a condensed matter seminar, and these Nobel Prizes become liabilities because it has been 40 years since the discovery of fractional quantum Hall effect. So what possibly new I could say about it today? So, so the situation is actually worse because in addition to these 2 Nobel Prizes, there are at least 2 more Nobel Prizes that are at least directly related to quantum Hall effect. One is the 2010 Nobel Prize on graphene, which of course honors the works that demonstrated that we have Dirac fermions there. But the way that we knew these are Dirac fermions in graphene is because of this unusual integer quantum Hall sequence. I guess I can't really do pointer, but I guess you can see on the right-hand side, this half integer sequence in the appropriate units of 4e² of h. This shift of 1/2 to the integer is due to this pi Barry phase when you have massless fermions going around the Dirac point. So the most recent quantum Hall related, or at least the quantum Hall inspired Nobel Prize was, of course, that one given out in 2016, shared among Solis, Haldane, and Kosterlitz. And of particular importance is Solis' insight that the quantization of the Hall conductance is because, or its origin is actually topological. It's because the Hall conductance is actually a topological quantum number, or topological invariant. And I actually copied this picture from the Nobel website, which of course everybody here knows what they mean. Essentially, the different plateaus correspond to different topological quantum numbers. But I guess the real impact of Solis' insight is that topology is actually essentially everywhere, not only in condensed matter physics, but also actually in other branches. And since then, the notion of topological phase and topological order have been actually widely used in everywhere in physics. Okay, so quantum Hall effect give birth to the notion of topological phases, which of course essentially every condensed matter talk has something to do with these days, including mine today. On the other hand, topology is actually not the aspect that I'm trying to emphasize here and for today's talk. In a way, I'm actually trying to go in a orthogonal direction. Here, of course, the quantization due to topology gives rise to universal physics. But as we're going to see, there's actually very interesting non-universal physics in quantum Hall liquids. And some of the non-universal physics is actually associated with geometry, not just topology. So this is the point that Haldane emphasized in a very insightful paper some 11 years ago now, which to me started this, this whole subject, which I actually also spent the last 10 to 11 years working on. So the first specific result I'm going to actually present and convince you is that actually this geometry of fractional quantum Hall liquids is not just a conceptual construct, but actually has direct experimental consequences. In fact, they can be measured experimentally and has been measured experimentally. So it turns out this geometry or geometrical degree of freedom not only exists, but they also have very unusual quantum dynamics. And pointed out by Haldane and Song and their collaborators early on, that the quantum fluctuation of the geometry gives rise to a spin-2 excitation, very much like graviton. And we took the liberty, some of us at least, took the liberty to call them gravitons in this context. And the second result I'm going to present is that these gravitons can also be excited experimentally and probed using acoustic waves, which actually act in some way like gravitational waves. And the last set of results, which are particularly, well, to me, particularly interesting and relevant to states or systems of current interest, namely this 5-half system, which actually Adrian and I collaborated on many years ago, we actually complete the circle and now tie the geometry and geometrical excitations back to topology, because the nature of the topological phase at 5-half is still unsettled as of today. And I'm going to try to convince you that these gravitons have a very special property that they are chiral. And turns out the chirality of these gravitons will tell us, at least to constrain the topological order behind them. Okay, so that also serves as an outline of this talk. So let's again start from the very beginning, which is this plot. So different plateaus correspond to different topological orders. And in the words of your, I guess, next town neighbor, Xiaogang Wen, they can be described pictorially using some kind of dancing pattern. So let me actually start with the integer quantum Hall effect, where the dancing pattern is particularly simple. Basically, every dancer is just dancing around her own loops under two constraints. One is, of course, the quantization rule associated with the lambda levels. Each loop in the lowest lambda level, for example, has to enclose one flux quantum. And the other, of course, is Pauli principle, because we have electrons, which are fermions, and everybody is constrained to dance around her own loop, and you are not allowed to step into your neighbor's territory. And okay, I'm not going to actually say too much about the left panel. Everybody, I think, knows what I'm trying to say. Basically, despite the fact that the electrons are running around loops and not going anywhere, there are these chiral edge states that actually are responsible for the dissipationless and quantized Hall transport. Now, much more interesting is the fractional dancing pattern, let's say in particular for the laughing state. So there, because the filling factor is lower, each electron has more room to actually dance around. So in addition to the two rules, of course, the integer liquid has to obey, you have more room to go around, but now you want to actually also lower the electron-electron Coulomb interaction. So you want to stay away from each other. And the rule here is that as you are dancing toward a existing dancer, you have to dance around her in 3 steps. Or more precisely, you dance around her in a bigger loop that encloses 3 flux quantum. So this already gives you a hand-waving way to understand why you have fractionally charged quasi-particles for the fractional quantum Hall liquid like 1/3. So imagine there is a pillar in your dancing floor. And obviously, the dancer don't want to bounce into that pillar. So what do you do? Well, you do the same thing, which is when you approach the pillar, you actually dance around it. But there is a quantization rule, as I said, for the size of the loop. It has to enclose one flux quantum. So one flux quantum. So some charge gets actually depleted from this pillar. Now you try to measure or calculate how much charge this topological defect in this dancing pattern has. Well, compare that to the electron right here. For each electron, you have to dance around her in 3 steps, or with a loop with 3 flux quanta. But this one, you only need to use 1 loop. So therefore, the charge that is depleted from this pillar is actually 1/3 of that electron charge. So that's a pictorial way to understand why this new dancing pattern gives rise to new quasi-particle excitations, which are actually fractionalized in charge, but you can actually even come up with more sophisticated argument why they can actually have fractional statistics. And these are the reasons quoted in the Nobel Prize for the fractional quantum Hall effect. Okay, so actually another way to represent the dancing pattern is a picture that's shown here, which Steve Gerving and I chose to use as the cover of our recent condensed matter textbook, which was published 3.5 years ago now, and has been adopted by many institutions worldwide. So this is, I guess, a 15-second commercial break in this talk. So let's get back to the business. I don't want to abuse my opportunity here. Okay, so we can actually go further in the dancing pattern list. So in addition to the trivial integer dancing pattern, the Laughlin more complicated but more interesting dancing pattern, we can have even more sophisticated dancing pattern, which I would characterize as more real dancing pattern. So here, the rule is that 2 dancers can get as close as that is allowed by the Pauli principle. But the rule now is if there's a couple that is actually close together and doing their intimate things, a 3rd dancer has to stay away. And more precisely, the 3rd dancer has to stay 4 steps away. So obviously, this is a very good dancing rule that not only gives rise to this, I'm going to say a little bit about that towards the end, non-abelian topological order and associated non-abelian quasi-particles, but I think it's also a very good rule for social behavior. So I like it very, very much. Anyway, so everything here is still topological, okay? So these different dancing patterns correspond to different topological order. So where is the geometrical aspect? So as Haldane pointed out, you can actually distort, for example, in the Laughlin case, this dancing loop, let's say from a circle to an ellipse. As long as you don't change the area, you're fine. So why would you want to do that? Well, for example, there could be systems where the Coulomb interaction is, let's say, stronger along the x direction than the y direction. Then you would like to stay away more along the x direction than the y direction, and you would actually, let's say, stretch this loop more along the x direction at the expense of the y direction. Or more relevant to what I'm going to talk about later, you could have anisotropy that is more intrinsic in the electron band structure. So there, the natural way to actually dance around loops are not circular anyway, okay? So then you might end up distorting for that reason. So, but the constraint, the topological constraint there still is that this loop has to enclose exactly 3 flux quanta. And Haldane called it area preserving diffeomorphism. So you can change the shape of your loop, but you're not allowed to change the area. Okay, so one immediate consequence of this observation is that unlike what you have been told, that Laughlin's wave function is such an amazing variational wave function that it does not contain a variational parameter. There is actually a hidden variational parameter, which is actually this geometry of this shape. So the original Laughlin wave function is completely isotropic, let's say correspond to the original circular dancing loop, but you can actually distort it. So we have actually, shortly after Duncan's original paper, constructed this entire family of what we call Laughlin states, where the original Laughlin wave function is a very special member of. And here are two examples. The original Laughlin wave function has a correlation hole, which is completely circular. That's the right panel. And that has, let's say, anisotropy primed gamma 0 equal to 0. But on the left panel, we constructed a particular member of this entire Laughlin state with a anisotropy, let's say, primed 1/2. Whatever that means, it's not so important. But now you see a clearly distorted correlation hole, but with the same area. But the unfortunate thing is that this distinction between, let's say, two different members of this entire Laughlin state, they have the same topology. So you cannot tell the difference between them by looking at this, transport plot, because the quantization of the plateau and the vanishing of the longitudinal or dissipative transport is tied to the topology. It's not sensitive to the geometry, even though it's still, well, it is there, but I'm going to convince you it is indeed there. And it's too universal and therefore boring. So then the question is, how can we actually explore the geometrical aspect of the physics? And in a way, we have to actually destroy the topology to actually make the geometry aspect manifest. So the way to do that, that's not the only way, as we're going to see, but one way to do that is to actually recognize that we have a whole sequence of quantum Hall plateaus. And in some school of thinking, let's say in terms of James' composite fermion construction, they are all states formed by the composite fermions, and they end up at this 1/2 state, which of course here in Boston, I don't need to tell you how important and how interesting it is, but it's actually compressible. So if all of these states have this geometrical aspect, then so should this 1/2 state. And my first proposal is actually precisely to go to this 1/2 state and try to explore the geometry there. And I'll tell you how. So again, here in Boston, I only need to be very brief about the physics of the composite fermions. So you start with the electrons, okay? And of course, they form their Fermi surface. But now you turn on a strong magnetic field and put the filling factor at 1/2, which means you have 2 flux quanta per electron. But one way to think about this 1/2 state is to pretend that the flux is not provided by the external magnetic field, but actually is attached to each electron. So now the composite object is your composite fermion. And it's a fermion because it inherits the electron Fermi statistics, but the barrier phase coming from the 2 flux quanta is actually 1. So it doesn't change the statistics. So as a result, when you go to high magnetic field, the state that formed is actually a composite fermion Fermi liquid. Okay, so you have a Fermi surface both at 0 field and at half filling. So a very interesting question that Shagan's group asked early on is, well, what if I start with an anisotropic crystal where the Fermi surface for the electrons is anisotropic? What happens to the corresponding composite fermion Fermi surface? I'm not going to get into the experimental details other than saying that there are very well developed ways to actually do the Fermi surface measurements for the composite fermions. And that's the same technique that Mansour has been using. Other than mention that there are 2 different ways to actually control the electron band dispersion of an anisotropy. The first way to do it is to apply an in-plane magnetic field, which for those of you who are familiar with quantum Hall effect knows that's often used to actually control the Zeeman splitting or the Zeeman coupling to the electron spin. But it also has an orbital effect because of the finite well width. And that, of course, has an effect on the dispersion. And the other is to actually just to distort the crystal by string, okay? So in either case, it actually leads to a modification of the electron effective mass tensor, which is a rank 2 tensor, which for reasons that's going to become very clear easily, become clear very quickly. I write that as a metric tensor, okay? So what did they find? Well, not surprisingly, they found that when you start with the electron distorted or anisotropic Fermi surface, the composite Fermi surface is also anisotropic. So that's not surprising because they have broken the rotation symmetry. But what was somewhat, at least somewhat surprising, was the fact that the composite fermion anisotropy is always less than the electron anisotropy, and often much less. That is actually inconsistent with the kind of naive picture I was presenting, which is just pretend that the flux is not doing anything. So in the zeroth order of, let's say, the Halperin-Reed mean field theory, the external flux and the flux carried by the composite fermion just cancel each other out, and the composite fermion has the same effective mass tensor as the electron, so they should have the same anisotropy. And that's indeed some people have predicted actually afterwards, but that's not how it worked out. So the first result I'm going to actually present is actually this Fermi surface geometry for the composite fermions is precisely Haldane geometry. Okay. The reason for that I'm going to actually present, but at least this gives you a different perspective about this area preserving diffeomorphism. So for more traditional condensed matter physics, we are familiar with this Luttinger theorem, which says that when you change band structure or essentially anything, you can change the shape of a Fermi surface, but you cannot change its area because there's this Luttinger sum rule. And this is exactly the area preserving aspect of this Haldane geometry. But now you may be a little bit surprised or even confused because the geometry I was talking about earlier is the real space geometry. But the Fermi surface geometry is a momentum space geometry. So how are they related? Well, it turns out in the magnetic field, there is actually a duality between real space and the momentum space. If you solve, let's say, I mean, I happen to know Adrian and Eugene are both teaching undergraduate quantum mechanics. I'm sure one of you, if not both, will tell them how to solve the Landau problem. You usually start with the Landau gauge, where you have, let's say, momentum along y direction being a good quantum number. But then you find that it's the y momentum that tells you where the electrons are in real space along the x direction. So basically, in the magnetic field, the momentum space geometry and the real space geometry are just a 90-degree rotation of each other. Okay, so that's the claim. So now let me try to actually justify this claim. So I justify this claim by presenting an exactly solvable model of this geometry change. Okay, so what's the model? Well, we usually work in the high field limit where the Landau level spacing is infinite. So you can forget about Landau level mixture and focus only on the two-body electron-electron interaction. Okay. Now, again, for someone teaching quantum mechanics, you would never give the student a problem that has no kinetic energy, but only interaction energy, because that's too easy, right? But of course, this is not an easy problem. And the difficulty, of course, comes from the fact that you have to project the two-body interaction to a particular Landau level, usually the lowest Landau level. Not necessarily all the time, but usually the lowest Landau level. So when you project a two-body interaction to a given Landau level, you have to replace the electron coordinates by the guiding center coordinates, which don't commute with each other. The different components of the guiding center coordinates don't commute with each other. So the intrinsic difficulty of a quantum mechanics problem, namely you have non-commuting variables, is still here. It comes from the Landau level projection. Now, where is the information about the band structure or electron dispersion encoded? Well, that's encoded in the Landau level form factor. And the Landau level form factor is particularly simple for the lowest Landau level, which is the Gaussian, which of course is tied to the fact that the lowest Landau level wave function is essentially the harmonic oscillator ground state wave function, which is the Gaussian wave function. Now, the band anisotropy is actually encoded in the anisotropy of this form factor because the kinetic energy and the potential energy of the harmonic oscillator really maps onto the x and y components of the Landau level problem. Okay, so given that, let me actually choose a particularly nice model, which is a Gaussian two-body interaction. So the nice thing about the Gaussian, of course, is Fourier transform is also a Gaussian. But let's actually start with the isotropic Gaussian interaction. So now I have an isotropic Gaussian in momentum space, which I have to combine with this anisotropic Gaussian, which results yet in another Gaussian whose anisotropy is somewhere in between. Okay, so the final Hamiltonian will have an anisotropy parameter that's between 1, which is the isotropic case, and the anisotropy of the band structure. Okay? But I haven't told you what my filling factor is yet. This result applies for any filling factor. So when I put in 1/3 filling, that will result in a distorted or anisotropic version of the laughing-like state. But when I put this at half filling, it will give you a Fermi C state. But now the Fermi C will have this anisotropy. And that already qualitatively explains this less anisotropy that experimentalists found when you go to half filling. And this result has been also confirmed numerically. So partly motivated by this analytical result, Shagan's group actually now later on did more detailed quantitative study of the relation between the electron anisotropy and the composite fermion anisotropy. And they found this empirical relation, namely the composite fermion anisotropy seems to be very well fit to a square root dependence to the original electron anisotropy that they call alpha F, I guess F for fermion. Okay, CF is for composite fermion. So, well, how do we understand that? Well, one thing that they noticed, which I wasn't actually aware of, is if you actually look at the anisotropy that I gave, you can actually factor out the square root, which of course they wanted to explain their result. But the remaining factor cancels out exactly if you choose the range of the Gaussian interaction to be exactly the magnetic length, which turns out not to be an unreasonable choice for the following reasons. So of course, I mean, the Gaussian interaction has a range, but the real interaction is the one of our Coulomb interaction, which has no range. But in my original paper, I already pointed out that actually because of the finite well width, there is actually a hidden range in the Coulomb interaction, because as the electrons approach each other in the quantum well, the Coulomb interaction starts to saturate when their separation become the well width. Now, typically, the well width is something like 100 angstrom, somewhere between 100 and 200. And that is also the typical scale for the magnetic length. So choosing the range of the interaction to be the same, or at least close to the magnetic length, is actually very, very reasonable. And there are other reasons I'm not going to get into, and numerically that turns out to work out as well. So I think it's fair to say that with this exact soluble model, we have actually a both qualitative and quantitative understanding of the origin of this geometry, and at least not necessarily at the quantum Hall states, but actually in the parent, actually composite fermion Fermi liquid state, you can actually probe them directly. But what about the dynamics of the this geometry of geometrical degree of freedom? So it was pointed out actually from different people, from different perspectives, actually going all the way back to Deng Li and Shuchen Zhang in a paper in 1990, that there is actually a quadrupolar mode, okay, in the fractional quantum Hall liquid in long wavelength limit. And these modes are essentially this graviton that I mentioned earlier, because a quadrupolar mode carries spin 2. And other people have actually approached this from the perspective of possible pneumatic instabilities of fractional quantum Hall liquids. I think Ichiro was actually involved in some of the early work when you were working with Eduardo. So now the question is, what is the excitation spectrum of a fractional quantum Hall liquid, let's say the 1/3 Laplacian liquid, and where is this graviton excitation? So we know very well this magnetoroton or GMP mode at finite wave vector. But it remained unclear for many years what happens when you go to the long wavelength limit. Because if you look at these spectrum numerically, very often it actually enters the particle Hall continuum, and whether there is still a sharp excitation or sharp mode at long wavelengths or the limit or not is not clear. So if there is a graviton, then you should have a fairly sharp excitation at 0 wave vector. So the question is, how do you actually probe it? Okay. Now the difficulty with that is we are used to doing electromagnetic, using electromagnetic probes, but there is actually a mismatch in the sum rule because the electromagnetic wave is basically photons. Photons carry spin 1, but here we have a spin 2 excitation. So how can you actually excite a spin 2 excitation? Well, my proposal is to use gravitational wave, which of course we know is propagating everywhere all the time, including here in this room. Okay, so it's obvious, obviously. But it wasn't so when I actually made this proposal, which was in August of 2015, some 45 days before the first arrival of the LIGO signal. So that got me into quite a bit of referee trouble because the referees didn't think there was such a thing called gravitational wave. Of course, I mean, I wasn't really thinking about the LIGO gravitational wave. What I was thinking about was actually some condensed matter analog of a gravitational wave, essentially actually acoustic wave that induces strings that are fluctuating. And that actually behaves like gravitational wave because, as I did earlier, I wrote the effective mass tensor as a metric tensor. Well, what gravitational wave does is to induce oscillations in the local metric tensor. Well, what acoustic wave does is to induce local crystalline oscillations, and that modifies the local effective mass tensor. So there are different ways to do it. The simplest way, which is the only way I'm going to focus on, is this panel A, where you propagate the acoustic wave perpendicular to the interface, which is where the electron gas lives. So that induces fluctuations in the XY plane of the effective mass tensor because it actually induces local crystal distortion. And you can actually control the frequency. So I'm not going to go through the details because it's actually quite similar to the model that I presented earlier. You can work out very easily the way this, what I call gravitational wave, couples to the electron gas. And indeed, as expected, this is a D wave coupling, which means it will only couple to D wave or spin 2 excitations. So if you measure the absorption spectrum of the acoustic wave, you are really measuring the spectral function of this D wave operator. And if a graviton excitation or sharp graviton excitation is there in the long wavelength limit, it should show up as a resonance kind of peak in the spectral function. So while I was actually fighting my losing battle with PLL, I recruited my collaborator Ed Rezai to actually calculate this spectral function. And indeed, he found very sharp graviton peaks for the Laughlin state for both for the bosonic version and for the fermionic version, but for small sizes. And we didn't publish them, but the similar results was published by this group in a slightly different context. Now, the reason we didn't publish this calculation is because this D wave operator, which actually represents the coupling between the string oscillation and the 2D electron gas, does not actually reveal a very important property of the graviton, which is its chirality. So here we are in 2 dimensions. We have the momentum equal to 2, but there are 2 possible polarizations, either +2 or -2. So instead, what we focused on later is to actually the chiral version of these D wave operators. Well, there are 2 of them, one for -2 and one for +2. And we found for the Laughlin state, you only have the -2 chiral gravitons. You have 0 spectral function for the +2. Okay. Now for Coulomb interaction, it's quite similar. You do get some +2 chirality, but the weight is much, much smaller. Okay. Now, I said that you cannot use photons to excite these gravitons, but I was actually not being very accurate in that statement because I was assuming that you are actually only considering a single photon process. There, of course, there's a mismatch in momentum, so you cannot excite a spin-2 excitation. However, you can consider a 2-photon process. One of them is a Raman scattering, where you actually take a photon, and then you emit a lower energy photon. So then the 2-photon process can actually excite the graviton. So the Raman experiment was indeed done many years ago by Aaron Pinsak's group. And they did find some response. And we compared our calculation with the results back then and did find reasonable agreement. However, they didn't use polarized photon. So as a result, they were not able to resolve the chirality of these gravitons. So we already proposed in our paper that you should be able to actually resolve the chirality of these gravitons by using a polarized photon to repeat the Raman scattering experiment. In a very exciting recent development, Song and Nguyen pointed out that actually the Raman spectral function turned out to be exactly the spectral function that we actually calculated earlier. So that's not only a qualitative statement, but also quantitative information that is actually revealed by this measurement that hopefully will be carried out in the near future. Okay, so now let me actually explain why for the Laughlin state I only have -2 gravitons but not +2 gravitons. So again, this has to understand that we have to come back to the topology or this dancing pattern. So another way to actually describe this dancing pattern is when you look at a pair of electrons in the Laughlin state, they have to have a minimum angular momentum of 3. Okay, so that's sort of the dancing rule. Okay. However, a graviton, when you create a graviton, basically what you're doing is you turn a pair with angular momentum 3 into a pair with angular momentum 1. Well, which is actually, so I'm recycling this plot, which I used to represent the Morley dancing pattern, but now for a different purpose. Namely, now with a graviton excitation, what you have, crudely speaking, is a pair with relative angular momentum 1, which is not allowed in the Laughlin state or the vacuum of the graviton. So during the process, you decrease the relative momentum, angular momentum from 3 to 1. That results in a net change of -2. Okay, so that's why the chirality of the graviton in the Laughlin state is -2. However, you immediately see that this actually is really tied to the chirality of the original Laughlin dancing pattern. So if you go, let's say, from 1/3 to 2/3, then you would have a Laughlin state formed by holes. The holes actually have the exact opposite chirality. So then everything has to be reversed. So there you'll find that the corresponding graviton will have chirality +2 instead of -2. So immediately one experimental prediction is that if you use, let's say, polarized Raman to probe the graviton chirality, you'll find -2 at 1/3, but a +2 at 2/3. Now, of course, we know exactly what the dancing patterns or topological order is for 1/3 and for 2/3. So that's not really going to give us any new information. Okay, so this is repeating what I just said. Graviton chirality is reversed for particle conjugated states. But now let's actually come to the very frontier of the quantum Hall research, or at least one of them, which is the state at 5/2, which is a subject that AJ and I worked on many years ago. At that time, we didn't know the exact nature of the state. One of the leading candidates was this Morley state, described by this dancing pattern. But the complication there is that there are many other competing dancing patterns or topological orders. One of them is precisely the particle conjugate of this Morley state, called very imaginatively the anti-Pfaffian state. But recently, people have actually proposed, and it has actually received quite a bit of experimental support, this pH-Pfaffian state, which is actually particle symmetric. So we don't know at this moment which state is actually realized at 5/2. So our proposal is actually using the chirality of the graviton excitations, you may be able to actually pin down one or at least limit the possible dancing patterns. So if you neglect somewhat extrinsic effects like lambda level mixing, disorder, etc., you should have actually perfect particle symmetry at half filling. So that's very, very special for half filling, which is half full is the same as half empty. Okay, unlike 1/3 when you do the particle conjugation, you go to 2/3, which is a different filling factor. Here, 1/2 becomes 1/2 again on the particle transformation. Now, if you start with a perfectly particle symmetric Hamiltonian, you are going to get a particle symmetric graviton spectrum. And this is actually the case for the Coulomb interaction, which without any external perturbation is particle symmetric. You get exactly the same spectral function for both +2 and minus chirality. However, we know from numerics, Adrian actually contributed to some of them, that by perturbing this half filling, this particle symmetric state with particle symmetry breaking perturbation, you can tilt the system to either Pfaffian or anti-Pfaffian very, very easily. So if we add a small positive three-body interaction, which breaks particle symmetry, it favors the Pfaffian state. And we found that now the spectral function is dominated by -2, just like the Lofting state. So the Moride state or the Pfaffian state is like the half-filling version of the Lofting state. Basically, that's the next member in this entire read-reside sequence. It has the same chirality as Lofting state, but if you actually do the opposite, which is more likely to be experimentally relevant, namely a negative three-body interaction that favors the anti-Pfaffian state. So that actually tilts you towards the hole-like state, which has the opposite chirality. And indeed, in this case, we found that the spectral function is dominated by +2 chirality instead of -2 chirality. Yeah.
How do you read those spectral functions? I mean, the chirality from them.
Okay. So you do separate calculations. Yeah, I was rushing a little bit. So I have two operators, one with -2, one with +2.
Mm-hmm.
So I do the calculation for the two of them separately.
Mm-hmm.
Well, Ed did the calculation for the two of them separately.
Mm-hmm.
If you have particle symmetry on the particle hole transformation, you map one for the other. So you get exactly the same thing.
Mm-hmm.
But without particle symmetry, we find that always you have one dominating the other. So experimentally, it should be very easy to tell which chirality is dominant.
Right.
Yeah. So so what we propose in this most recent work is that if you use polarized light to perform Raman scattering at 5 halves, you may be able to tell whether it's a Pfaffian or anti-Pfaffian that is realized by inspecting the chirality of the response. On the other hand, well, okay, so we don't have a very good microscopic model for it, but on the other hand, if for some reason it's the particle Pfaffian that is actually realized, then you should see more or less symmetric spectral function between these two chiralities. So therefore, in the end, we find that we may at least be able to use the geometrical excitations by studying these geometrical excitations to actually pin down the underlying topological order. Okay, so these are the specific results that I wanted to present in this talk. So just I have a few minutes. I probably was going through things quickly and people didn't get a chance to interrupt and ask questions, but there will be some time. So, but let me just offer some closing remarks. So there is actually still life beyond topology in condensed matter physics in general, for sure, but even in quantum Hall effect, which of course got this topological business started in the first place, and geometry actually is a crucial ingredient in this endeavor. And I presented some specific results, okay? which depending on what your research topic is today, may or may not be particularly relevant, but I guess the main message is that these geometrical degrees of freedom and the geometrical excitations in turn informs us about the topology of the system. Okay, so therefore, even if you are still mostly thinking about topology or topological physics, you may actually be helped by actually thinking about the geometry aspect as well. Now, so of course, the detection of the real gravitational wave 7 years ago now, almost exactly 7 years ago, right? This is August. Sorry, this is October. Yeah. Of course, was a huge deal in astrophysics because they pretty much exhausted all the electromagnetic probes of the universe, and the gravitational wave gives them a different way to actually observe the universe. To some extent, the same thing could be said about condensed matter physics, right? Most of the condensed matter experiments use electromagnetic probes to probe the crystals or whatever system. But maybe we should also start to think about some kind of geometrical or gravitational response, but of course not real, again, not using the real gravitational wave, but actually some analog of them, which may be useful. And I hope I gave you some examples that this may actually be the case. And at the very end, maybe as a sort of a propaganda, perhaps the fractional quantum liquids can actually even give us a platform to study some version of quantum gravity, because the elementary excitations are these gravitons. And they gave us some way to actually study their own interactions, their own dynamics, how they interact with each other, and how they interact with matter. Thank you very much.
Thank you for such a beautiful talk and nice overview of the topic. Time for questions. Any questions from the live audience here? Yeah, Swati.
It might be a very nice question, but what are like the energy ranges in those Raman experiments?
Yeah, so they are sort of hidden here. I didn't emphasize the quantitative aspects. So these are in units of E squared over H for a Coulomb interaction, which typically is about 100 Kelvin. Okay, so if you translate it into frequency, that's something like 10. Well, okay, let's bring it down. So we're not talking about 100 Kelvin range itself, but the energy scale associated, let's say, with the fractional quantum Hall gap is typically about 1/10 of that. So that brings you down to about 10 Kelvin. Okay, so that's something like 100 gigahertz. So it's a gigahertz to terahertz range. Yeah. So actually, since you asked that, let me just make this comment. So Raman is fine. So this frequency is a bit low for optics, but it's a bit too high for acoustics. So I'm kind of stuck in the uncomfortable, inconvenient place. So I originally proposed the acoustics. That frequency is a bit too high. But when you talk to an optics person, terahertz would be much better than gigahertz. So, but I guess with some stretch, these are doable. Yeah.
Like, can we use like optical phonons instead?
So optical phonons distorts the lattice in a more complicated way. So I mean, qualitatively speaking, I think the answer should be yes. But this particular spectral function, I'm not so sure is still appropriate. But you're right that you can use higher frequency phonons. Yeah.
So one more question.
Sure.
So for acoustic waves, like, do you need acoustic waves with finite chirality?
So that's the point. So the point is that the usual acoustic wave, they are just some oscillation, right? So that's like linearly polarized. So it couples to the electrons with this, well, the x squared minus y squared coupling, which does not reveal the chirality. So that's its disadvantage. That's why we didn't even bother publishing this result, because we feel that what's more important is this chirality, which photon can do very easily, but you have to use polarized photon. Yeah.
Thank you.
Yeah, but I mean, we think useful to think about whether there's a chiral version of the acoustic wave coupling. I haven't really thought much about it.
There could be, I mean, for optical photon sign off.
Yeah. Right. Thank you.
I have a quick question.
There's a question from the audience, yeah, online. Please go ahead. Who's talking?
Hi, yeah, it's Vadim. Hi, Kunyang. Nice talking.
Hi, Vadim. Good to see you. Yeah, long time no see. Yeah.
Likewise. I'm just curious. What kind of gravitational physics is interesting? Since I'm just going back to your last, hopefully not throwaway comment.
Yeah, right. So, okay, so that's a very good question, and I'm glad it's you who is asking it, not a real gravitational physicist. Of course, I mean, these gravitons are not the real Einstein-Hilbert graviton, right? Because we don't have general coordinate covariance. So it's like these, using a slightly stretched analogy, it's like we are studying vector bosons instead of gauge bosons. Okay, so the real gravitons are more like a gauge boson, but these are more like massive versions of them. On the other hand, these systems, in principle, should be able to tell you something how the gravitons interact with each other. You can easily imagine sending two gravitons and ask how they would actually scatter and how they would, let's say, exchange chirality or mix chirality, et cetera, et cetera. So that's one kind of question you can ask. To me, a more relevant and maybe more sort of realistic question is how. Let me see. Oh, okay, let's go further back. How the gravitons interact with the matter field. So here we have these gravitons, but we also have the Laughlin quasi-particle quasi-holes. So these are like the matter fields. So you can also ask how these gravitons scatter with the Laughlin quasi-particles. So that would be a process that is mimicking the graviton-electron interaction, for example. I mean, I'm just giving you some examples. I don't have a grand scheme of a systematic study of gravitational physics in this platform, but I'm just asking some specific questions. Yeah.
Can I ask a naive question, sir? Can I condense these gravitons? Is that a pneumatic instability if I condense gravitons?
Yes.
On the polarization?
I allude to it. So, okay. So again, I'm really glad that you asked, and Yizhi is actually here, who actually I think is better person to answer your question than me. So I'll say it, and you should feel free to jump in and comment. So for your friends, well, they're also my friends, but especially they're your friends, the pneumatic instability is triggered by the softening of the graviton and going all the way to zero energy. Now, it turns out actually there are models we found recently, not from our work, but from other people's work. You can actually pull the graviton out of the particle continuum. So they're not actually buried in the particle continuum, although it's still not so easy to condense them. But the premise of the work on the pneumatic instability is not only such an excitation, such a mode exists, they actually condense. And that actually leads to the pneumatic instability.
Okay, that's easy.
Easy in what sense? We haven't found a model to do it yet.
Well, no, to understand.
Okay. Yeah, but I'm not aware of a model that actually does that. Yeah. Yichi, are you?
Yeah, the problem is we have proposals on pneumatic phase transitions on compressible or incompressible fractional quantum Hall state where the pneumatic instability actually have interference with the GMP mode, which is your particle mode here.
Yeah.
And the GMP mode collapse to zero. This is how a pneumatic quantum Hall appear. But the problem is, what is likely to happen is we also have that at a rotor minimum.
Right.
Finite momentum, and it is possible that before that.
Yeah,
become
it gets preempted. Yes.
Zero.
So some kind of weird crystalline state. Yeah.
Line or
Takes over first.
This
Yeah.
is what is usually observed.
Exactly. Yeah. Vadim, were you able to hear what Ichi was saying?
Yep.
Okay, good. Yeah.
Yep.
All right. Any other questions from the online audience? Feel free to jump in. All right. If not, we thank Kunyan one more time.
Thank you.
Thank you, everyone. See you next week.
Thanks for the initial.
Okay.